So I'm Stephen Forrester. I'm the principal engineer at DMA Engineering. So this webinar is about why I care about building envelopes in luxury residential buildings. So our involvement, we have been designing electric heating systems for over 15 years. I first read about ground source heat pump systems when I was getting my master's degree, and I just thought they're the coolest thing ever. They really tickled my hippie bone. So we've been designing those type of systems for about that long. So we have designed several net zero projects. This is not only where our passion lies, but also our genius. So if we think about taking a building, we take a plot of land that actually gives life, dig it up, put in a building that consumes energy. So that building should at least be net zero. So it's producing as much energy as it's taken in, and hopefully be net positive. But mechanical systems are the largest user of energy on site. So we got to figure that out. How can we make those not be the largest user of on site or reduce those significantly? Three main considerations are key to success for luxury residential projects is the owner's project requirements, the building envelope. And so why do we care about that? Well, let's make the mechanical systems as small as possible. It really makes high efficiency mechanical systems affordable. And as a mechanical engineer, we get to do some pretty cool stuff when we can make the mechanical system small, and allows us to have a little bit of budget to do some pretty cool stuff. So that's one reason. We also got to understand the site constraints, right? So if we're trying to make a building net zero, can we put in a ground source heat pump system? Do we have the room? What's the solar? Can we get enough solar photovoltaics to offset all the energy? Is that possible? What do we got to do? So that can take it a next level on what we got to consider. Design through final commissioning. It's our philosophy here at DMA Engineering. We just cannot, do the energy modeling and a design and throw it over the fence and let the installing contractors and everybody have it, right? So we stay with the project for 9 months after the homeowner moves in and take care of some commissioning items in the background. We deploy software with that. And so, for instance, we recently just troubleshot a pump that had a loose wire, and the pump was working intermittently, and we could actually see that on the data. And so we were able to get to the mechanical contractor to go out there and say, hey, there's a problem with this pump. They looked at the wiring, they found that the wire wasn't all fully terminated, and it was just intermittently working. They tightened it up, boom, it's off to the races. No big deal, right? If we hadn't been monitoring that, it could have been doing that for a lot of time, start and stopping that pump, wear the pump up prematurely, or until the wire came done. But we were actually able to take care of that totally remotely. So that's pretty cool. So what does the building envelope have to do with mechanical systems? Well, the building envelope affects the mechanical system size, right? So that's what we were talking about, trying to make it as small as possible. Insulation and windows are typically cheaper than the mechanical system. Again, energy consumption, more energy to overcome the gains and losses with the mechanical system. So if we're thinking about a building, right, energy's coming in the summer through the solar radiation and just a hot ambient air. It's trying to get into that system. We have to continually add mechanical system to overcome those losses. And what does that mean? Well, if we're doing forced air systems, we're moving a lot more air to make that happen, right? In the winter, the opposite's the case. Energy is trying to leave the building, and we got to keep putting energy back into the building. Well, what does that all have to do with anything? Well, it comes down to occupant comfort. All that energy in and all that energy out is going to drive the occupant comfort. We as engineers, we look at something called operative temperature, and that determines comfort. I'm not going to get too far into that, but overall, it's the air temperature and the radiant air temperature that's going on. So we got to be considered with that. So sounds like we got somebody that's not on mute. If you can mute, that would be great. So occupant comfort. So we're looking at that occupant comfort with the air temperature and the radiant temperature is what kind of drives that. And it gets a little bit more nuanced in that, but I'm not going to get too far on that. But that's what we're looking at is occupant comfort. So if you got to have a huge mechanical system to overcome these things, a lot more energy is going in, a lot more energy is going out. Their occupants aren't going to be there. And then what does it do to renewable energy systems if we have to meet some type of code, right? All these ins and outs are being overcome. And if we're trying to hit a HERS score or a net zero goal or whatever it may be, we have to put more energy from a renewable energy source to meet these codes. It makes it harder to overcome. And then indoor air quality, right? So if we have a really good building envelope with really well insulated walls, but we didn't get the air barrier just right, and now all air air always has a little bit of moisture in it, right? So moisture is going to be moving through that wall assembly, And if it gets to the right spot, it can condense. Now we got a point for mold issues. You can have a really well insulated building, but if there's holes in it, air is just going to get in there. It's actually going to take energy out of the space or energy into the space, another in and out, and we can have more problems with mold contaminants in there. So getting the air barrier right is important. Again, with contaminants in the space, if air's coming through weird cracks and everything getting into the space, we can have an ERV or an HRV circulating that air and filtering it as much as we want. But if we don't have those airs coming into it, it is, and we're only trying to maintain what's in the space, it's so much easier to do. And again, it's back to making the mechanical system as small as possible. So what is the building envelope? So in a nutshell, it's the wall insulation, it's the roof insulation, it's the window U value, the window solar heat gain coefficient, it's the floor insulation, the foundation insulation, the water sealing, the air sealing, and the thermal breaks. So when I say wall insulation and roof insulation, we're tending to mean that with all the R value, if you will, of all the components that make up that. It's just not the insulation itself, it's that full assembly. What does that full wall assembly look like? That's kind of what we're saying. So I may have changed that slide just to say wall assemblies and roof assemblies, but that's what we're looking at, right? What is the U value? What is the thermal performance of that? And then all the way down to, how are we air sealing the building and water sealing, right? So we got to make sure that, water's not getting into it, and air that is leaving the building, how is it leaving the building? Is it going in a controlled way that we want it to go, right? So that we've actually engineered a solution so that is working the way we want it to go. So wall systems. So we need to consider the wall to roof and the wall to glazing plays into the value of wall insulation. So if the building on the right has a lot more roof area than the building on the left. So it may be in this particular instance that there's more roof surface area than the wall insulation or the wall surface area. So the roof insulation may have the bigger bang for the buck than the wall insulation. The one on the left with the modern architecture, it's a flat roof. But there's going to be a lot more wall surface area than there is going to be roof surface area. So the biggest bang for the buck is probably the wall insulation. So we just got to consider where is the biggest bang for the buck. Not one thing fits in because not all architecture is the same. So we just need to be evaluating what is the proper solution per that architecture. So wall systems have more interactions with other exterior systems. Details on thermal breaks and air sealing become more complicated. So if we think about a wall, right, it's going with the foundation, floor systems, and then the roof system. Well, each one of those on their own, a roof is just itself, and then how it interacts with the wall systems. The same with the floor, right? It's just a floor and the wall, not with any other system. So we have to understand those connections, and we're losing energy. There's some big code changes that are coming along. I was at the Cherry Hills Village Builders Conference just a couple of weeks ago. Hope Medina with Kum Shota was there, was giving a presentation on these differences between the code, between the 2015, 2018, and the 2021 IECC. So for our climate zone here in the Front Range of Colorado, the 2015 IEC says, and the 2018 says, you need an R20 bat insulation in the wall or a U value of 0.060 if you're doing the performance path. The 2021 IEC is going all performance paths, so you have to have a U value of 0.045. They do give you a table they call it an alternate method for the R value, but it's R20 plus 5 continuous, right? So if you're already kind of doing good construction already, this, having a 5 inches exterior insulation is not, or an R value 5 exterior insulation is not going to be that hard to do. But if you're not, there's some complications that we'll get into on another slide, which is continuous insulation and how that all goes about. But you can get to the spray foam for 5.5 wall with some type of flash and fill, right? So, and I think I did the math and it comes out to be like, 4.5 inches of spray foam, and then you can do a flash and fill and it'll get you the numbers that you need to be for spray foam. Continuous exterior insulation, right? So you got to do that R5 to get you to those numbers, or you can go to a 7.5 inch wall for conventional bat. So now you're doing a 2x8 framed wall, and that'll get you that U value of 0.045, and then possibly even go to double wall systems. And again, in most cases, this should not, the going to the continuous exterior insulation or trying to hit these wall values, for most people, this shouldn't be that hard to do because we've already been doing it, right? Because we've been building better than code. Code is a minimum. We got to keep that in mind. Code is just a minimum. So we shouldn't, let's go bigger than the minimum. So these changes should not be a big deal to most people. Now, The theme with what's going on in Colorado is the governor's office is making it that they're putting in the Colorado energy codes coming along, right? And it's going to say either take the 2021 IECC or the 2024 IECC, whichever is more restrictive. Hope was saying in her presentation that the 2024 IECC is going to be a lot more restrictive than the 2021. So Cherry Hills Village is running to adopt the 2021 IECC in June so that they don't have to go to the 2024 for X amount of time, right? So they're bringing stuff up forward. There's going to be some, agency, some building departments are going to lag behind that, and we're going to have to jump up to the 2024. So the leap between the 2018 IECC to the 2024 is going to be like a gigantic leap. So let's just try to get ahead of that if we can by building better as it is already. And if you get a chance, go look at Hope Medina's presentation. I'm sure she'll be doing it multiple times. It'll help you understand what's going on in the code much better than I. So she's really into the code stuff where I understand the code, but she's like in there on the committee. So I encourage you to go look at her stuff. So architectural designs that start with a 10 to 12-inch wall will alleviate negotiations later regarding wall thicknesses. So we get into a lot of instances where the wall is designed as a 2x6 wall, right? And then we're like, well, can we go with this insulation? Which pretty much puts us right into, we got to do exterior continuous insulation because all the areas have been calculated by the areas with a 2x6 wall. But if we just start by designing a 10-inch or a 12-inch wall, we don't have to go into negotiations. What can we do? Can we make this happen? All the space planning has already been designed out, and we know what it's going to take to make a thicker wall to make it happen. I think there's a lot of advantages on especially luxury residential homes to use a little bit of thicker wall. It gives that architectural look that we see that gets built up with a lot of, exterior trim or interior trim and exterior trim on it. We can get away with maybe a couple smaller pieces of trim and actually give that heavy weight that we're trying to achieve with a lot of these. Window sills can be put in a lot easier with a thicker wall. There's just a lot of things I think we can do with a thicker wall. That architects gives them a lot more room. But if we can start with the 10 or 12-inch wall, that's it. Now, there is some things going on, Boulder's having some issues when we go with like a double frame wall. Where do they, will they allow that exterior to be in the setback, take it from the interior dimension to be within the setback, and then what's on the exterior to be in the setback area so that they don't have to get into the constraints they have with the infill. I'm sure Denver's going to be the same way. The building departments haven't thought all this out yet. So that's why a lot of people go within the sheathing, because that's where the code is, and then we can hang the continuous insulation off there. So very nuanced to how you can get into this stuff. But if we can start on paper in schematic design with a 10 or 12-inch wall, I think we're going to be already halfway there to making a very good energy efficient building. So let's talk about wall systems and spray foam insulation. Spray foam is not the panacea we all hope it to be. And I'm one of those. When spray foam first came out, flash and fill was the best thing to do. It was great, right? It gave us high R values. But then, air sealing, all the other stuff that comes along with spray foam, it's still out there. I think it's still used as a catch-all. It's going to solve all the problems, but does it really? So proper specification, architect or energy consultant, how many times is it just called out on the plans, R6 per inch spray, closed cell spray foam insulation, right? I mean, we see that all the time. There's no other specification in there of what actually the spray foam is supposed to be. And here, this is straight from the BASF technical data sheets on spray foam. So a couple things to point out is humidity and dew point. No spraying should be done when the ambient temperature is within 5 degrees of the dew point. Now, so, let's think about, the typical day when that's happening. Who's measuring that on a job site? I mean, I don't think anybody's ever caring about what that is. Other couple things to be pointing out is it says, normal substrates, 20 degrees F to be spraying on, but then it says heat strength materials is 30 degree F. How many luxury residential construction projects have a ton of steel in it with wood framing? Is anybody paying attention to what the temperature of the steel is at versus what the wood temperature is? Nope. They just show up and start spraying. Steel has a different expansion rate than wood. When it cures, are we getting cracks in the foam? How's all that, how's it all interacting when it's all going together? Who's paying attention to these numbers? I'm going to guess there's probably not a lot of people on the job site that are really paying attention to this. Minimum pass thickness is a 1/2 inch. Maximum lift thickness per pass is 2, 4, and 6 inches. You know, I mean, how many people are actually making sure that they're spraying the foam in those controlled manners and going back over it? I think the other one to really be taking a look at is the optimal thickness range, right? 1/2 inch, 2 inch, 2.5, 3.5, 5, and 6, right? Depending on the spray foam. How many times do we see a specification that says spray foam insulation to an R70 wall, right? So it's 6 inches at a 6.5 inch foam. That's an R39. So how are we getting an R70? I mean, that's got to be 12 inches of spray foam insulation. The manufacturer says the optimal thickness range is 6 inches. There's internal heat that can build up within the spray foam insulation when it's put on there. Are we getting voids in the spray foam? Are we really achieving that R70 wall that's specified on there by using spray foam? So I just think there's a lot of, I think the spray foam is great in certain applications. And I'm not here, to bash the whole thing. I think it still needs to be used, but I think we just use it randomly without fully understanding what all it takes to do that. Here's a great resource on a YouTube video you can go look at. They point some of the same points out that I did on how to spray foam. They go into a little bit more things on what to see on site inspections, but that's another great one I encourage you to go look at. So continuous exterior insulation, right? So the great thing about continuous exterior insulation is it eliminates thermal breaks. This is the one reason I really like continuous exterior insulation. It increases the R value of the wall without shrinking the interior space, right? Because it's all exterior. It comes back to that, where do you measure the wall sheathing and what can be in the setbacks and all that. But it is difficult to go greater than 2 inches. Special screws and hangers are required. Then the other thing we always run into, hey, can we do 2 inches of exterior stone? Everybody's like, well, the mason doesn't want to hang stone off of that. And we're like, well, what's it going to take to make us be able to hang stone off of this? Are we going to do a brick ledge and have a drainage plane that's supporting all the masonry? Do we do a cut stone put on there? It always becomes an issue on what needs to happen with it. Here's a very, very good detail from 475.com. It's a great detail in their copyright. They say, take this detail, use it any way you want, use it as a starting point, right? They just give you all these details. So anybody that's listening to this webinar or watching this webinar, I cannot encourage you to go, grab this screenshot, go to their webpage, download all their details and have them somewhere. And when you need to do a wall section, go look at one of these details. There's just a lot here, a lot of really good information, a lot of good starting points. And where necessary, specify their product, right? They're giving you something, their products are good. They're really trying to, this is all out of like the passive house world. Some of the stuff that you're seeing here, you don't need to go as extreme, right? We have a couple of details that we've started here, and we've taken them back a little bit for some of the projects we're working on. So we've used them as a starting point. Really good. I just can't encourage you enough to go get those. So wall systems, double wall, right? If you can frame one wall, why can't you frame another wall? So I think for me, I'm leaning this a lot more to double wall construction in just how we go through, because it's pretty straightforward. There's not a lot of little things that we don't have to get 100% right, because we're framing walls, and your good framers know how to frame, right? And so it's right in their wheelhouse. We're just framing 2 walls together, adding some voids. It's easiest to achieve the highest R value, right? We just have to increase that thickness of that wall, keep adding in insulation, like a cellulose or whatever, we can get there. You can hang stone off the exterior. And the other thing is the continuous insulation air is inside. So it just makes it a little bit easier to do the installation, do coordination issues. It's not all this complicated stuff to make it all happen. But I just think it's just something to be considered in our projects. We cannot consider double wall if we're already starting at a 2x6 wall, right? So we got to be drawing those walls thicker in our schematic designs to make that happen. I do want to point out, like over here on the right, this detail, right? You can just see how much information they give you on a detail. If in a high performance building, we need to be providing details. So the guys in the field, guys and gals in the field, know how the building is supposed to go together and what it's supposed to look like. Doing specifications and saying it's in the spec, I mean, really, the guys in the field are not going to be reading that specification a bunch, right? They're just not. They're going to be looking at the details. And as with the details, you can see all the steps and how everything has to go together, how to get an air barrier. The air barrier has to be continuous. Well, how do I do that? You have to lay the air barrier down, put the floor system on it, wrap it back around, put the wall on top of the air barrier, and then fold the air barrier back up onto the wall, right? Now we've got a continuous air barrier through this. But if it's not laid out, they're going to get to like step 5 and go, uh-oh, we forgot the air barrier. Now what do we do? You can't really go back and replace that air barrier. So having a good detail that lays everything out for everybody in the field just solves a lot more problems. Again, please go download these wall and floor details from 475. All right, so so roof insulation, right? So wall to roof area, roof may be better impact than the wall. We kind of talked about that already. Where to put the insulation on the ceiling or bottom rafters. So these 2 pictures take me back to the pop top we did at my dad's house. This picture on the right looks exactly what we did. We put in some knee walls on his attic, changed the pitch of the roof and then, insulated it. And so very, very common to what my construction did back at my dad's house in the 90s. But again, it gets the point across, right? We got insulation on the bottom of the rafters. There's no vent here in the roof system, maybe a little bit of a problem. But anyways, you see that the insulation's right on the bottom of the rafter. Here, the one on the left, it's blown cellulose on top of the gypsum ceiling. So we need to be considering where we're putting in ducting, right? Just mechanical equipment going in here. That can help understand, what type of insulation systems we're actually putting in. Maybe it's better to put stuff on the bottom of the rafter, gives us an interior volume for us to be running ducting and all that and everything that needs to go in there. Sprinkler systems. We worked on a project where they had a sprinkler head froze. They did some overframing and they ended up with a little bit of an air leak, and it ended up freezing a sprinkler head on one of these cold snaps that we had. Most of the times, we got down to like -12. So most of the times they may have gotten away with it, but it was such a cold snap that they actually ended up having a sprinkler head freeze. And it was just a couple of overframes that happened and the insulation didn't get exactly where it needed to be. That was on a commercial project, but the same thing can happen on very complicated luxury residential where we got roofs overlaying it and we're doing, it gets complicated on if you're doing an overframe on a roof or what have you, that you can get a little bit of a void. So where do you put the insulation to eliminate that needs to be considered. So using more insulation may increase the weight, right? So R70 cellulose on gypsum, considering strapping on 12 inches on center. So that's 12 inches on center here, right? Gives you more area to screw to. So like if you're doing a ceiling, rafters that are 24 inches on center, and now you're putting more weight on top of the gypsum, you may want to strap it. And that gives you, you could put screws on whatever center you want, typically 12 inches on center. And that can give you the extra carrying capacity of the gypsum to do that. So you don't end up with nail pops. We have one project where the GC is actually going to go ahead and just put an OSB on the bottom of the rafters. He feels that's more confident. He's more confident that they're not going to get any nail pops on that particular project. But you need to consider that, right? So let's talk about code changes, right? 2015, 2018, we can get an R49 in the ceiling or a U value of 0.026. Now with the 2021 IECC, it's saying you got to go to R60 with the U value of 0.024, right? So now we're going. R60 is the standard. How are we going to deal with this? So just the rafter truss heel height. I just can't believe we're still talking about this after all these years, but 14 to 15 inches is the minimum to meet code with cellulose. That's like our minimum that we should be considering on our rafter truss heel height. That should be standard across the board. Everybody's doing that. But we can't be seeing smaller than that to be doing good construction anymore. All right, so glazing. So the problem with well-insulated walls is windows. We are literally cutting holes in the insulation. But who wants to live in a windowless room? I'm working right now. I'm looking out a window, right? We all want to have windows to look out, look at the views. It's kind of important, especially on luxury residential homes. Views are typically a big part of the residence. But high-performing windows are becoming the norm and not the exceptions. So, back in the day in 2013, we did an analysis on some triple pane windows, U value of 0.2, solar heat gain of 0.19, and they were 2x over a 0.3 and a solar heat gain coefficient of 0.3. 2022, kind of the same specifications, and it's a 1.1 extra expense over a U value of 0.3 and a solar heat gain of 0.3. We did another project, I think, since this, and I think the architect said there's no difference in the cost price, or the general contractor said there's no difference in the cost of going to a window of this performance over the other window. So, I mean, it just makes sense to go. So the lower the U value is the way to go. And then choose the correct solar heat gain coefficient. And what does the energy model say? Maybe it's better to go with the higher solar heat gain coefficient than a lower one. In our climate zone 5 here in Colorado, the code says it's not required to have a solar heat gain coefficient. But anybody that's built the house that has really west facing glazing, and a lot of it, knows you want to have a solar heat gain coefficient on that window to not overheat that room. Back in the day, it was the thing to tune the windows. One window would be you'd have lower solar heat gain over here and higher over here. I think the thing with that is the tint plays into how you look at the windows, right? You look at one, it's going to have a different color than the other one. So you're going to end up with all these different things that are playing into it. So that's gonna cause problems. So, and then the window leak rate needs to be considered. If we're trying to really build really tight building envelope, the leakage of the windows is starting to become a bigger issue, and we're starting to consider that more and more on what that window leak rate is. So floor installation. So here's a typical floor, and tough connection with thermal breaks. We end up with a lot of discontinuity. Every engineer hates to hear the word discontinuity. It causes a lot of problems in math, and it causes a lot of problems when we're doing any type of modeling. Discontinuity will cause something to break. So we don't like to see discontinuity. So your thermal envelope, your air barrier, and your water barrier should be continuous, right? So here's a couple of details where you can see how the heck do we make this, continuous? There's the details, when it was drawn, these do not show how to make a continuous air barrier with these particular details, and they need work. So yeah, just need to think about, where are we going to put in a thermal break between our concrete, our exterior concrete, in our insulation. How can we put in some thermal breaks to make this all a continuous layer through here? And who's detailing this stuff out, right? So this one here, I don't think it ever got detailed out correctly on exactly what was supposed to happen with it. We did a little FEA, expressed to why they needed to be doing it. And again, FEAs get into very complicated connections, and where does it all look like? And that may be what the project requires, and you should be able to go that extra step to make that all happen in it. But it's the most important thing is to make sure your air barrier and your thermal and your water layer are continuous at your floor connections. And how does that look like? So floor insulation above and below grade, tough connection with thermal breaks. We talked about that. Here's a couple of details kind of just showing how to do it. The one on the left here, this one is definitely from 475. Again, a really good detail, kind of lays out what needs to go where, how to do this. You don't need to go the full way, but if you just use some of what they're telling you in your projects, it's going to help you get so much further along. Here's this detail here from an architect. Great detail, tells you, everything's called out, bright 3XXP, R15, 2 lasers, static joints, what it all needs to make up. Here's a detail for us, right? This is an older one. It's saying R10 that we're calling out right here to eliminate that thermal break, right? Theoretically, you would like to see the wall moved over so it's more continuous. There's a little bit of a discontinuity right there. In engineering, we call that a singularity. Again, don't like discontinuous stuff, and we don't like singularities, but got a little bit of a singularity there. It's better than nothing. So that's kind of that detail. Infiltration. So 2015, 2018 infiltration code says 3 air changes per hour at 50 pascals. The 2021 IECC is going to say 3.0. Is Hope brought up in her presentation. It says 3 air changes per hour, where there was nothing. If the guy were to write down 3.5 air changes per hour, the code official really couldn't say no because it's still within 3, right? It's a rounding error, which is, that's a trick that I've never seen played. But now it says 3.0 air changes per hour. So they've actually tightened that up that you're going to have to do it. So let's just talk a little bit about air changes, right? 2 air changes per hour at 50 pascals. Yeah, it's easy enough. We have to be paying attention to some details to make sure we're going to get there. 1.25 air changes per hour at 50 pascals. It's pretty difficult to do. A larger residence has more areas to leak. So it's maybe not as hard on a larger house versus a smaller house where you don't have as much area to tighten up the building envelope. But then we go to the next level, right? 0.6 air changes per hour at 50 pascals, and that's a certified passive house certification. That's the whole other next level. All the little air sealing details is getting taken care of. Everything's going to that next level when we're going down in the air changes per hour. But here's a way to think about your leakage rate, your infiltration on a building, right? So a code building should be built to outlast the mortgage, right? Without any maintenance. So if we think about it just in that regards, right? So if you do maintenance, it's going to outlast the mortgage and it's going to be more resilient. If you start decreasing the infiltration rate, that building becomes more resilient because we're not having air entrainment going through. We're not having condensation issues. It's going to be so much more energy efficient than the other house. You're building a house that's going to outlast the mortgage and then some, right? So Passive House is saying that their houses are like 100-year construction on their own. Now, how much maintenance is there to make that happen? It's not going to be as great as it is to take a house from 3 air changes per hour to get to that 100-year mark without having to go through and maybe, windows and siding and all that other stuff. The Passive House should have a lot less maintenance and get to that same point and fully outlast the mortgage of the home. So it's very important to be thinking about, like when you're thinking about tighter building envelopes, you're actually building a better resilient building that's going to last so much more longer than the thing. But tighter building construction is inexpensive to achieve, but requires more construction coordination. It's not, the materials are not that expensive in and of themselves, but it's a lot more coordination to make sure that we're staging air barriers correctly, making sure that everything's getting sealed at the right time, doing blower door test at the frame stage. It's hard to do a full-on blower door test on a 13,000 square foot house. But in a lot of construction, we're phasing the construction. Let's phase that construction so that we can do a blower door test. Let's work in the very beginning of how we're building this house on how we're going to stage certain things so that we can do a frame stage blower door test, maybe on the master suite, right? And then we move to the next part of the house. And then we keep moving through the house and doing these tests. And by the time we're all said and done, we've tighten up all those little infiltration areas. And we know that when we get to the final blower door test, we're going to hit a certain number. When we just run to the races and do the final blower door test, it's far too late for us to go back and try to do any air sealing. So it's just making sure the coordination is done in the beginning on how actually we can stage construction so that we can do the proper testing and make sure that we're going to hit the numbers we're going to. And then good air sealing details is a must. That 475 gives you so many more details. It's going to help the guys in the field, guys and gals in the fields, actually build a really, really good building envelope. So let's have details, right? It's good to have good specifications as a CYA, but the details is where everybody's going to look and it's where they're going to go. So let's just make sure that we're actually starting to do really, really good details for everybody to be able to build stuff. So let's talk about the building envelope. Why, as a mechanical engineer, do I care about the building envelope? So here's just a couple of slides here that we've just kind of grabbed from certain paybacks, and they're not all the same thing. So you're just going to have to look at some of the numbers, but here's a 1-inch exterior insulation. There's no payback on it, right? And you look at this and you go, well, why would you ever do it? Well, this particular analysis was done for Boulder County, where we have to hit a certain code compliance, right? This building needs to be net zero. So baseline home is going to require 80 kilowatts to make it all happen, right? So then if we come down here to upgrading the roof, we're knocking off 2 or 3 kilowatts off the solar photovoltaic. If we come down here to the 1-inch exterior, we've knocked 5 kilowatts off the cost of the system. When you add that 5 kilowatts back into this life cycle cost, that 1-inch exterior insulation has an instant payback on itself, right? So you got to look at these things holistically on exactly what does it take to do. And, here we are with just all upgrades with the baseline HVAC system. We're looking at 70 kilowatts to make it happen. We ended up going with the ground source heat pump system on this building. I think we're down to 15 kilowatts is what it's going to take to make this house hit the code compliance and net zero requirements on this. So cost, right? Here's the cost thing. Here's the externality of what's going to do to the solar photovoltaic. Let's add that back in here. What does this actually look like? That tells one story. The other story is, let's talk about occupant comfort, right? So here's our operative temperature. So we say if we're going to reduce the operative temperature by 0.5 degree, we're going to give that, whatever we're analyzing 1 point, right? So it's going to take away 1 point. So the baseline starts at 0, and then we just keep adding points up as the operative temperature gets closer to what we want it to be. So if we do all of the things that we want to do, upgrade windows, exterior insulation, and upgrade roof from R55 to R70, this looks like, we give it a weighted average of 5. What's the architectural impact for all of these above? Are we going to have to worry about, adding 1 inch exterior? What does that actually do to how things are stacking up? Because the wall wasn't designed to be 10 or 12 inches. It's like, oh yeah, we got plenty of room to deal with that. It's like, no, oh God, what do we do about this detail, right? It's already drawn at 10 or 12 inches. And we say, hey, let's just make the wall 6.5 or 7.5 inches thickness. It's so much easier, right? Everybody's gonna be, oh, that's a no-brainer. Why don't we go to 2 inches? It's, the conversation becomes a lot easier. And then we, construction impact, how much harder is it going to be to do some of these? What does it do to the HVAC impact? How much are we reducing the cooling load? How much are we reducing the heating load? Financial impact gets weighted in here. Carbon, right? We weigh carbon in our stuff and it kicks out, all right, this is what you should do, right? So the windows in this particular one was like a no-brainer to do. And again, I think the cost difference on the windows, whereas financial impact was like a 1 or something. I mean, there was a little bit with the windows. It wasn't much. So that's what did it. Or it actually, the financial impact on the windows was so quick, we gave it a 1. So that's what weighted it over versus all the other ones. But again, once you add back in all the solar, all the upgrades here, if you were to look at, we went from 70 to 80, you use 350 a kilowatt, that's $35,000 to do all these, all the insulation stuff we talked about just got paid for. So you got to look at it holistically, right? It's just, how does each one of these things play? You just can't look at it and go, oh, it'll never pay back. Well, not necessarily. Let's talk about all these other things that are at play here, is how you have to be talking about the building envelope. And in luxury residential homes, you can't just say on the last project we did this, so we're going to do that over here, because the architecture is going to be different. The site's going to be different. There's so many different things that come into play that need to be evaluated each on their own, because they are a luxury residential project. So key takeaways. Good building envelope is key to a small mechanical system. That's why we care about the building envelope. Also, occupant comfort goes way up when we have a smaller mechanical system, right? Where the inputs and outputs aren't as great with the small mechanical system, which drives occupant comfort. Yeah, efficiency of mechanical systems may need to be considered to reduce the offset. That comes down to, like, what we were talking about on the other side. What does it do to the solar photovoltaics? What does all this happen, and how do we make all that happen? And then look holistically. One size does not fit all. I talked about that. And then trade-off between the building envelope mechanical systems and renewable energy systems. You have to be doing that on each and every single project. I just don't think we're doing it good as professionals if we're not doing something like that for our clients. We're not giving them the quality of service that they deserve to do. All right, question and answers. Lena, if you want to field any questions from the chat, let me know what they are. That'd be great.
All right. Anybody has questions, please put them in the chat. Don't see any yet.
I answered them all. Woohoo! All right, then. There's no questions. Thank you all for attending. Thank you for your time. Reach out to us with any questions. More than happy to discuss your project. Anything we can help out on, maybe given any of the resources we presented, point you in the right direction, just feel free. Here's all our contact information. Just reach out to us on anything. We're more than happy to help bring really cool projects to fruition. So thanks.